Hey there, stargazer. Welcome back to another journey through the cosmos, where we explore the universe's most fascinating mysteries while you drift off into peaceful sleep. Picture this somewhere out there, orbiting a distant star. There's a planet so enormous that if you could somehow place it next to Jupiter, our solar system's giant would look like a tennis ball beside a beach ball, a world so massive, so inflated, that its very existence defies our fundamental understanding of planetary physics. Scientists didn't just discover it, they discovered it shouldn't exist at all. Tonight we're going to meet the biggest planets ever found, worlds that challenge everything we thought we knew about how planets form, how large they can grow, and what's even possible in the vast expanse of space. And if you're enjoying this cosmic journey, I'd really appreciate it if you'd hit that like button and subscribe to the channel. It helps more people find these stories about our incredible universe, and it lets me know you want more deep dives into the wonders of space. All right, let's begin. For nearly 400 years, humanity had a constant in the night sky: Jupiter, the king of planets, the undisputed champion of size in our cosmic neighborhood. When Galileo first turned his primitive telescope toward the heavens in 1610, he discovered 4 moons dancing around this massive world. And in that moment, he realized we weren't looking at just another wandering star. We were witnessing something magnificent, a planet so large that it had its own miniature solar system. Think about what that meant to astronomers for centuries. Every textbook, every astronomy guide, every lecture about our solar system began with this fundamental truth: Jupiter is enormous. It's 11 times wider than Earth. You could fit 1/300 Earths inside its volume. It contains more mass than all the other planets in our solar system combined. When you looked up at that bright point of light moving slowly against the background stars, you were seeing the biggest planet there was. That wasn't just a fact, it was cosmic law. I want you to imagine being an astronomer in, say, 1950. You've spent your entire career studying Jupiter. You know its great red spot, a storm larger than Earth itself that's been raging for centuries. You've calculated its mass, its density, its gravitational pull. You've watched its moons orbit in perfect Keplerian harmony. And in your mind, in everyone's mind, this is what the maximum planetary size looks like. Sure, theoretically, there could be planets around other stars, but they'd probably look like ours, right? Jupiter represented the upper limit of what a planet could be. But here's the thing about the universe: it doesn't care about our assumptions. It doesn't read our textbooks or follow our carefully constructed theories about how things should work. The universe just is in all its wild, excessive boundary-breaking glory. The first crack in Jupiter's crown came in 1995. 2 Swiss astronomers, Michel Mayor and Didier Queloz, detected something orbiting a sun-like star called 51 Pegasi, about 50 light-years from Earth. They weren't looking at the planet directly, that technology didn't exist yet. Instead, they noticed the star was wobbling ever so slightly, pulled back and forth by the gravitational tug of something massive orbiting around it. When they calculated the numbers, they found something that made them check their instruments again and again. There was a planet there, and it was huge, about half the mass of Jupiter. But that wasn't the shocking part. The shocking part was that this Jupiter-sized planet was orbiting its star once every 4.2 days. Let me put that in perspective. Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. This newly discovered planet was so close to its star that its year was shorter than a single week on Earth. The surface temperature had to be around 1800 degrees Fahrenheit. This wasn't just a new planet. This was an entirely new type of planet, something that, according to our models of planetary formation, shouldn't exist. They called it a hot Jupiter. And it changed everything. Suddenly, astronomers realized we'd been living in a bubble, making assumptions about all planets based on the only 8 examples we had in our solar system. It was like studying only golden retrievers and then declaring we understood all of dogs, only to discover wolves and chihuahuas and foxes and dozens of other canines we'd never imagined. The universe we were beginning to learn had far more creativity than we had given it credit for. The late 1990s and early 2000s became a gold rush of planet hunting. New telescopes came online, detection methods improved, and with each passing year, we found more worlds orbiting distant stars, worlds that were stranger, more diverse, and often much larger than anything in our solar system. Have you ever had that feeling when you learn something that completely reframes your understanding of the world? That moment when you realize the map you've been using is missing entire continents. That's what astronomy felt like during this era. By 2006, we discovered over 200 exoplanets. Some were small and rocky. Others were massive gas giants. Some orbited so close to their stars, they were being slowly vaporized. Others drifted in frozen darkness far from any warmth. Each discovery added a new piece to a puzzle. We were only beginning to understand, how do planets form? How large can they get? What determines whether a planet becomes a rocky Earth or a gaseous Jupiter? And then in 2006, a team of astronomers using a network of automated telescopes detected something in the constellation Hercules that would push our understanding even further. The star GSC 02620-00648 was dimming periodically like clockwork every 3.5 days. Something was passing in front of it, blocking a tiny fraction of its light. That something was about to become famous not just for its size, but for the fundamental questions it raised about the very nature of planets. But we're getting ahead of ourselves. To truly appreciate what they found, we need to understand how we find these distant worlds in the first place. Because here's the beautiful irony we're detecting. Planets we can't actually see, measuring worlds we'll never visit, calculating the size of objects so far away that their light takes over 1,000 years to reach us. How is that even possible? The answer lies in one of the most elegant techniques in all of astronomy, a method so simple in concept that ancient humans could have understood it, yet so precise in execution that it reveals the secrets of worlds beyond our wildest dreams. We're about to explore the transit method, the cosmic detective work that lets us weigh and measure planets across the galaxy. And once you understand how it works, you'll see why bigger planets were actually easier to find, and why that matters when we're trying to figure out which planet holds the record for the largest ever discovered. Because as we're about to learn, in the realm of exoplanet size is far more complicated than it first appears. The most profound discoveries in science often come from watching something disappear. A star dims by less than 1% for just a few hours, and suddenly we know there's a planet orbiting it, warned 400 light-years away. We can measure that planet size, calculate its orbit estimate, its temperature, and determine whether it's made of rock or gas, all without ever seeing the planet itself. It sounds like magic, doesn't it? But it's something far better than magic. It's physics-patient observation and the beautiful realization that even across impossible distances, nature leaves clues for those willing to watch. On June 6, 1761, hundreds of astronomers across the globe turned their telescopes toward the sun. They weren't looking at our star itself. They were waiting for Venus to cross in front of it, an event called a transit. This wasn't just astronomical curiosity. Captain James Cook would later sail to Tahiti specifically to observe the next Venus transit in 1769. Because by timing these transits from different locations on Earth, scientists could calculate the exact distance from Earth to the Sun, one of the most important measurements in all of astronomy. Think about that for a moment. By watching a tiny black dot crawl across the face of the Sun, they could measure the scale of the solar system itself. The principle was elegant in its simplicity. When Venus passes between Earth and the Sun, it blocks a small amount of sunlight. The Sun dims ever so slightly. By measuring exactly when the transit begins and ends from different points on Earth and using geometry that would have delighted Euclid himself, astronomers could triangulate Venus's distance from us, and from that, calculate how far away the Sun really is. The answer they eventually derived, 93 million miles, was astonishingly accurate given the technology of the 1700s. But here's what they couldn't have known. Back then, standing at their brass telescopes with their carefully calibrated chronometers, they were pioneering the exact technique we'd use 2.5 centuries later to find planets around distant stars. Fast forward to the 1990s. We knew theoretically that if a planet passed directly between us and its star, from our perspective here on Earth, it would cause the star's brightness to dip slightly, just like Venus dimming the sun. The problem was the scale. Venus blocks about 0.1% of the sun's light during a transit, but Venus is relatively large and relatively close. An Earth-sized planet crossing in front of a sun-like star would dim that star by only 0.008%. That's not 8% or even 0.8%. That's less than 1/100%. To detect that, you'd need instruments sensitive enough to notice if a single light bulb in a chandelier of 10,000 bulbs flickered for a few hours. And yet, astronomers built exactly those instruments. They had to, because the transit method offered something that other planet hunting techniques couldn't: the ability to measure a planet's size directly. When you detect a planet by the wobble, it creates in its star's motion. You learn about its mass. When you detect it by its gravitational lensing effect, you learn about its mass. But transits tell you how big the planet actually is, because the amount of light blocked is directly proportional to the planet's cross-sectional area. Let me paint you a picture of how delicate this measurement is. Imagine you're in a football stadium at night, and someone turns on a single floodlight. Now imagine they hold up a dime 50 feet in front of that floodlight. Could you, sitting in the stands, measure the tiny decrease in brightness caused by that dime blocking part of the light? That's essentially what astronomers do when they detect an Earth-sized planet transiting a distant star. Except the star isn't 50 feet away, it's trillions of miles away. And instead of a few seconds, they have to monitor it continuously for weeks, months, sometimes years, waiting for the planet's orbit to carry it across our line of sight. The geometry matters enormously here. For us to see a transit, the planet's orbit has to be aligned almost perfectly edge-on from our perspective. If the orbit is tilted just a few degrees, the planet passes above or below the star from our viewpoint, and we'd never know it was there. Think of it like watching a carousel from the side versus from above. From the side, you see the horses moving in and out, appearing and disappearing behind the central pole. From above, you just see them going in circles, never blocking anything. For planets, we need the side view. Statistically, this means we only see transits for a small fraction of all exoplanets. Maybe 1 out of every 100 planets happens to orbit in a plane aligned with Earth. But when we do catch them, the payoff is extraordinary. Here's where it gets even more interesting. The transit doesn't just tell us the planet exists and how big it is. The exact shape of the light curve, the graph of the star's brightness over time, reveals additional secrets. When the planet first touches the edge of the star's disk, the brightness doesn't drop instantly. It decreases gradually over several minutes as the planet's circular profile moves onto the star's face. This is called ingress. Measuring the duration of ingress tells us how fast the planet is moving, which helps confirm the orbital period. Then the brightness stays relatively constant. While the planet crosses the star's face, that's the full transit. Finally, there's egress, when the planet begins to leave the star's disk, and the brightness gradually returns to normal. But wait, there's more, encoded in that simple dip in brightness. If the planet has an atmosphere, some of the star's light will pass through that atmosphere during the transit. Different molecules absorb different wavelengths of light. By comparing the star's spectrum during the transit with its spectrum when the planet isn't blocking it, we can detect the chemical signature of the planet's atmosphere. This is how we've found water vapor, methane, and even hints of exotic molecules in the atmospheres of distant worlds. A tiny dip in starlight becomes a window into alien skies. Now, remember when I mentioned that bigger planets were easier to find? Here's why: the amount of light blocked depends on the planet's area, which goes as the square of its radius. A planet twice as wide as Earth blocks 4 times as much light. A planet 3 times as wide blocks 9 times as much light. Jupiter, being about 11 times wider than Earth, blocks roughly 120 times more light than Earth would. Those early planet hunters weren't being lazy by finding Jupiter-sized planets. First, they were working with the tools they had, and Jupiter-sized planets created signals strong enough to detect with the technology of the late 1990s and early 2000s. This created what scientists call an observational bias. It's not that most exoplanets are Jupiter-sized hot Jupiters orbiting close to their stars. It's that those were the easiest ones to find. They're big, so they block more light. They orbit close to their stars, so they transit frequently, sometimes every few days instead of once a year, giving us many chances to observe them. And they orbit fast, so we don't have to wait decades to confirm their orbital period. If you're going fishing and you only have a net with large holes, you're going to catch large fish. That doesn't mean there aren't small fish in the ocean. But here's what's remarkable: astronomers knew about this bias and accounted for it. They didn't just catalog the planets they found. They carefully calculated how many planets they were missing based on the limitations of their instruments. When the Kepler Space Telescope launched in 2009, specifically designed to find Earth-sized planets using the transit method, it stared at a single patch of sky containing about 150,000 stars and monitored their brightness continuously for 4 years. The data it collected revolutionized our understanding of planetary systems. We now know that small planets are actually far more common than large ones, but you'd never know that from the early discoveries. And this brings us to a fascinating question. When we talk about the biggest planet ever discovered, what are we really measuring? The planet that blocks the most light, the planet with the largest radius, the most massive planet. These aren't always the same thing, and the answer reveals something profound about the nature of planets themselves. Consider this: the planet we're about to meet, TAR-ES 4b, discovered in 2007, isn't the most massive exoplanet known. Not even close. But it is absolutely enormous in terms of physical size. It's so bloated, so puffed up that its density is lower than cork, actually lower than balsa wood. How is that even possible? How can you have a planet the size of a small star, but with the weight of, well, not very much at all? The transit method gave us the tools to find TAR-ES 4b. It measured its size with remarkable precision, but understanding why it's so big, that required us to completely rethink our models of planetary atmospheres, heat distribution, and the very mechanisms that determine how large a gas giant can grow. What we discovered challenged theoretical predictions and opened up entirely new areas of research into planetary physics. Because TAR-ES 4b isn't just big, it's impossible. Or at least it should be, according to everything we thought we knew. And when nature hands you something impossible, you have two choices: reject the observation or rebuild your theory. Fortunately, astronomers chose the latter, and what they learned rewrote the textbooks on planetary formation and evolution. Imagine holding a block of balsa wood in one hand and a planet in the other. Ridiculous, right? One weighs a few ounces, the other weighs more than all of human civilization combined. But what if I told you? There's a planet out there with roughly the same density as that piece of balsa wood. A world so impossibly light, so extraordinarily puffed up, that when scientists first calculated its properties, they literally went back and checked their math 3 times because they were convinced they had made an error. They hadn't. TAR-ES 4b exists orbiting a star in the constellation Hercules, and it breaks every rule we thought we had about how planets work. August 2007. The scientific journal Astrophysical Journal was about to publish a paper that would send shockwaves through the planetary science community. Georgy Mandushev and his team at the Lowell Observatory in Arizona had been using the Transatlantic Exoplanet Survey, a network of small automated telescopes designed to catch planetary transits when they noticed something strange about a star designated GSC 40262000648, located approximately 1/400 light-years from Earth. The star was dimming regularly every 3.55 days, which suggested a planet was orbiting it and periodically blocking its light. That wasn't unusual. By 2007, dozens of exoplanets had been discovered by then. But when the team calculated the size of the object causing those dips in brightness, they got a number that seemed absurd. The planet appeared to be about 1.7 times the radius of Jupiter. Not the mass, the physical size. This thing was enormous. Now you might think, okay, so it's a big planet. What's the problem? The problem emerged when they calculated its mass using a different method by measuring the tiny wobble the planet created in its star's motion as it orbited. The mass came out to only about 0.92 times Jupiter's mass, actually slightly less massive than Jupiter. Let me repeat that. For emphasis, TRES-4b is 1.7 times bigger than Jupiter in size, but weighs less than Jupiter. Do you see the issue? When Mandushev and his colleagues calculated the density mass divided by volume, they got a number that made them question everything, about 0.2 grams per cubic centimeter. To put that in perspective, water has a density of 1 gram per cubic centimeter. Jupiter, despite being a gas giant, has a density of 1.3 grams per cubic centimeter because gravity compresses all that hydrogen and helium. Saturn is less dense than water at 7 grams per cubic centimeter, which is why there's that famous thought experiment about Saturn floating in a bathtub, if you could find one big enough. But 0.2 grams per cubic centimeter. That's the density of styrofoam. That's lighter than cork. That's about the same as balsa wood, the lightest wood you can buy at a hobby store. Edward Dunham, one of the co-authors on the discovery paper, said something that perfectly captures the moment. TAR-ES4 appears to be something of a theoretical problem. Problems are good, though, since we learn new things by solving them. That's the diplomatic way of saying their discovery had just punched a hole through conventional planetary science. Here's why this was such a crisis. According to every model of planetary formation and structure that existed in 2007, TRES-4b shouldn't be that big. Gas giants form when a rocky core accumulates enough mass to gravitationally attract huge amounts of hydrogen and helium from the surrounding protoplanetary disk. As the planet gains mass, gravity should compress the gas, making the planet denser. Jupiter is roughly as large as gas giants get in our standard models because beyond a certain point, adding more mass just compresses the planet rather than making it bigger. It's like squeezing a balloon filled with water. At some point, squeezing harder doesn't change the balloon's size much. It just increases the pressure inside. So how do you get a planet that's nearly twice Jupiter's size but less massive? The only explanation is that something is actively preventing the atmosphere from collapsing under its own gravity. Something is pumping energy into the planet's atmosphere, keeping it hot and inflated, like a balloon that's constantly being reheated. The obvious suspect was the planet's star. TAR-ES-4b orbits its sun at a distance of just 0.05 astronomical units. For comparison, Mercury orbits our sun at 0.39 AU. This planet is 7 times closer to its star than Mercury is to ours. At that distance, the stellar radiation is absolutely brutal. The planet's day side faces temperatures around 1,800 Kelvin. That's about 2,180 degrees Fahrenheit, hot enough to melt iron. The night side is cooler, but still scorching by any reasonable standard. But here's the puzzle: when scientists calculated how much energy the planet was receiving from its star, and how much that should heat the atmosphere, the numbers didn't add up. The stellar radiation alone wasn't enough to explain why the planet was so inflated. Mandushev himself pointed this out in interviews. We actually looked at the energy which the planet gets from the star, and there's no way this can be the only explanation for how big the planet is. This kicked off what became a decade-long investigation into what scientists started calling radius inflation, or radius anomaly, in hot Jupiters. Dozens of theoretical papers proposed different mechanisms. Maybe the stellar radiation was being absorbed deeper in the atmosphere than expected, preventing heat from escaping efficiently. Maybe tidal forces from the star were generating internal friction heat, as the planet's shape got slightly distorted by gravity. Maybe there was some kind of atmospheric circulation pattern, creating a greenhouse effect on steroids that trapped heat. Maybe charged particles from the star's magnetic field were dumping energy into the upper atmosphere. Each theory had problems. Each theory could explain part of the inflation, but not all of it. And TRES 4b wasn't even the only planet with this problem. It was just the most extreme example at the time. Astronomers kept finding these bloated hot Jupiters, each one challenging our understanding of planetary atmospheres. Think about what this means from a physics standpoint. You have a ball of gas the size of which is being determined by a delicate balance between gravity trying to squeeze it smaller and heat trying to make it expand. On Earth, our atmosphere has a scale height, the altitude over which atmospheric pressure drops by a certain factor of about 8 kilometers. For TRES 4b, with its low gravity and high temperature, the scale height is enormous, maybe 1,000 kilometers or more. The atmosphere just extends outward and outward, fading gradually into space rather than having a sharp boundary. And there's another factor that makes TARES 4b even stranger. In 2008, a follow-up study discovered that the star it orbits isn't alone, it's actually part of a binary star system. The companion star is far enough away that it doesn't dramatically affect the planet's orbit, but its presence meant astronomers could make even more precise measurements of the system's properties. And those measurements confirmed it. TARES 4b really is that big, and it really is that light. You know what's humbling about this? The planet is 1/400 light-years away. The light we're seeing from its star left that system around the year 600 CE, when the Byzantine Empire was at its height and the Maya civilization was flourishing in Central America. We're watching ancient light-detecting dips in brightness that happened when our ancestors were living in a completely different world. And from that ancient light, we're calculating the density of a planet to a precision of a few percent. That's remarkable. But TARES 4b taught us something more valuable than just adding another exotic world to our catalog. It taught us that our theories were incomplete. We thought we understood gas giants. After all, we have Jupiter right here in our solar system to study. We'd observed it for centuries, sent spacecraft to it, even dropped a probe into its atmosphere. But Jupiter, it turns out, is a relatively cold gas giant orbiting at a comfortable distance from the Sun. It wasn't until we found planets like TARES 4b planets baked by intense stellar radiation, planets in extreme environments, nothing like what we see in our own solar system, that we realized how much we still had to learn. The discovery also revealed a common mistake in how we think about scientific knowledge. We tend to assume that if we understand something in one context, we understand it in all contexts. We studied gas giants in our solar system and thought we could extrapolate to all gas giants everywhere, but nature doesn't work that way. Physics operates the same everywhere, but the conditions vary so wildly that familiar objects can behave in unfamiliar ways. A cup of water on Earth behaves predictably. A cup of water in the vacuum of space boils and freezes simultaneously. Same physics, different conditions, completely different behavior. TARES 4b was like finding that cup of water in space and realizing our textbook understanding of water only applied to a narrow range of conditions. And the beautiful part, this realization didn't break science, it made it stronger. Astronomers went back to their models, incorporated new physics, tested new ideas, and gradually built a more complete understanding of how planetary atmospheres work in extreme conditions. By 2010, improved models that included more sophisticated treatments of atmospheric circulation and radiative transfer could explain most of TRES 4b's inflation, though some mysteries remained. The planet became a testbed for new theories, a place where we could check whether our ideas about atmospheric physics actually worked in practice. But TARES 4b's reign as the largest known planet was destined to be short-lived. Because the universe, as we keep discovering, always has something more extreme waiting to be found. Even as astronomers were publishing papers about TARES 4b, Other teams were analyzing data from their own transit surveys, finding their own bloated worlds pushing the boundaries of what we thought possible even further. And some of those planets would turn out to be even bigger, even lighter, even more inexplicable than the balsa wood planet orbiting that distant star in Hercules. The question became, just how big can a planet get before it stops being a planet at all? There's a planet out there that's currently being cooked so intensely by its star that it's literally twice the size of Jupiter while weighing barely half as much. Its atmosphere is so hot, so energized, that atoms are being stripped away and blown into space like sand from a desert dune. And here's the twist that defies everything: this planet orbits its star backwards. While nearly every planet in the universe spins in the same direction as its star's rotation, this world decided to break the rules. Welcome to the realm of the puffed-up giants, where physics gets pushed to its absolute limits, and planets exist in states so extreme they make Tauri S4b look almost normal by comparison. In 2017, a team of astronomers led by researchers from the Harvard-Smithsonian Center for Astrophysics announced the discovery of HAT P67b, and the numbers they published seemed almost like a typo. The planet's radius approximately 2.085 times that of Jupiter. That's not just big, that's monumentally absurdly, physics-defyingly massive in terms of physical size. To give you a sense of scale, if Jupiter were a basketball, HAT P67b would be one of those large exercise balls you see at gyms, the kind you can barely wrap your arms around. But here's where it gets truly bizarre. Despite being more than twice Jupiter's size, HAT P67b has a mass of only about 0.34 Jupiter masses. Let that sink in for a moment. This planet has roughly 1/3 the mass of Jupiter, spread out over a volume that's about 9 times larger. When you calculate the density, you get something around p.04 to 0.05 grams per cubic centimeter. That's less dense than aerogel, one of the lightest solid materials we can manufacture on Earth. It's approaching the density of air at sea level on our planet. Think about what this means physically. If you could somehow stand on a solid platform deep within HAT P67b's atmosphere, ignoring for a moment that the temperatures would vaporize you instantly, the gravity you'd feel would be incredibly weak. The escape velocity, the speed needed to break free from the planet's gravitational pull, is surprisingly low for an object this massive. Atoms and molecules in the upper atmosphere are constantly achieving escape velocity just from thermal motion. The planet is quite literally evaporating, losing mass to space in a continuous hemorrhage of gas. And this isn't speculation, we can observe it happening. When HAT P67b transits its star, astronomers using spectroscopic techniques have detected an extended atmosphere that reaches far beyond the planet's nominal radius. Hydrogen atoms stripped of their electrons by intense ultraviolet radiation from the star form a vast cloud around the planet. This exosphere is being blown away by stellar wind, creating a comet-like tail of escaping atmosphere. The planet is losing approximately 100 billion kilograms of mass per second. That sounds like a lot, and it is, but the planet is so massive that even at this rate, it would take billions of years to lose a significant fraction of its total mass. Now, why is HAT P67b so inflated? The answer lies in its orbit and its star's evolution. The planet orbits once every 481 days, at a distance of about 0.058 astronomical units from its host star. But here's the crucial detail. Its star isn't a normal main sequence star like our Sun. It's what astronomers call a subgiant, a star that's beginning to evolve off the main sequence and expand into a red giant. This means the star is actually brighter than it was a billion years ago, and it's only going to get brighter. The increased radiation is pumping enormous amounts of energy into HAT P67b's atmosphere. Imagine turning up the heat on a pot of water. As the temperature rises, the water molecules move faster, the steam pressure increases, and eventually the lid starts rattling. That's essentially what's happening to HAT P67b. except instead of water, it's hydrogen and helium. And instead of a lid rattling, the entire planetary atmosphere is expanding outward. The planet is absorbing so much stellar energy that its atmosphere has ballooned to an extraordinary size. But there's a ticking clock here. As the star continues to evolve, it will get brighter and hotter. Eventually, probably in a few 100 million years, it will swell into a full red giant, and at that point, HAT P67b's orbit might actually be inside the star's outer atmosphere. The planet won't survive that encounter. It will spiral inward. Friction with the stellar gas will heat it further, and ultimately it will be consumed entirely, vaporized into the star that created it. We're watching a planet in its death throes playing out over time scales so long that civilizations could rise and fall before the final act. Now, let's turn to another giant that breaks the rules in a completely different way. WASP-17b. Discovered in 2009 by the Wide-Angle Search for Planets Consortium, this exoplanet holds a distinction that still puzzles astronomers. It's one of the very few planets we've found that orbits its star in a retrograde direction, backwards compared to the star's rotation. In our solar system, all the planets orbit the sun in the same direction, and that direction matches the sun's rotation. This isn't a coincidence. It's a direct consequence of how solar systems form. The sun and planets all condensed from a spinning disk of gas and dust, and conservation of angular momentum ensured everything kept spinning in the same direction. Finding a planet orbiting backwards is like finding a car driving the wrong way on a highway. It's not just unusual, it's a sign that something dramatic happened to put it there. The leading theory for WASP-17b's retrograde orbit involves gravitational interactions with other planets in the system. Early in the system's history, WASP-17b might have had a close encounter with another massive planet. This gravitational slingshot could have flung it into an eccentric, highly tilted orbit. Over time, tidal interactions with the star would have circularized the orbit but preserved its backwards orientation. It's like a cosmic game of billiards where the planets are the balls and gravity is the cue stick. And WASP-17b is huge. Its radius is estimated at about 1.74 to 2.0 times Jupiter's radius, depending on which study you look at, making it comparable to HAT P67b in size. But unlike HAT P67b, WASP-17b has a mass of about 0. 49 Jupiter masses, still very low density, but not quite as extreme. The density works out to roughly 0.08 to 0.13 grams per cubic centimeter, somewhere between styrofoam and cork. What's fascinating about WASP-17b is that its retrograde orbit might actually contribute to its inflation. When a planet orbits in the same direction as its star, rotates tidal forces tend to circularize the orbit and align the planet's spin with the orbital motion. But when it orbits backwards, those tidal interactions work differently. Some theoretical models suggest this could lead to additional tidal heating, internal friction, as the planet gets stretched and squeezed by the star's gravity, which would pump extra energy into the planet's interior and contribute to atmospheric expansion. Both HAT P67b and WASP-17b orbit extremely close to their stars, receiving intense irradiation. But here's something many people misunderstand: the stellar radiation itself doesn't directly heat the deep interior of these planets. Light and heat from the star are absorbed in the upper atmosphere. For that energy to inflate the entire planet, it has to be transported downward somehow. And that's where things get complicated. One mechanism is atmospheric circulation. The day side of these tidally locked planets, they always show the same face to their star. Like the moon does to Earth, can be thousands of degrees hotter than the night side. This temperature difference drives powerful winds that redistribute heat. But these aren't gentle breezes. We're talking about supersonic jets of hydrogen gas screaming around the planet at speeds that would make Earth's hurricanes look like a light breeze. These winds can transport energy from the day side to the night side, and from the upper atmosphere to deeper layers. Another mechanism involves the interaction between stellar radiation and the planet's magnetic field if it has one. Charged particles from the star can be funneled along magnetic field lines into the planet's upper atmosphere, where they deposit their energy. This is similar to how Earth's auroras work, but cranked up to absurd levels. On Earth, auroras are beautiful light shows. On these hot Jupiters, the energy dumped by charged particles might be enough to significantly heat the atmosphere. There's also the possibility of tidal heating in the planet's interior. Even though these planets' orbits are nearly circular, they're not perfectly circular, and any eccentricity means the tidal forces vary slightly over each orbit. This flexing generates heat in the planet's interior through friction similar to how bending a paperclip back and forth makes it warm. For a planet the size of Jupiter, even a small amount of tidal heating could contribute significantly to keeping the interior warm and the atmosphere inflated. But here's what keeps scientists up at night. Even when you add up all these heating mechanisms, the numbers are still a bit short of what's needed to explain the most inflated planets like HAT P67b. There's still some missing piece of the puzzle, some process we haven't fully understood, or some mechanism we haven't discovered yet. And that's actually exciting because it means there's still fundamental physics to be learned. The study of these puffed-up giants has also revealed something profound about planetary evolution. These aren't static objects frozen in time. They're dynamic, evolving, changing over time scales of millions and billions of years. As their host stars age and brighten, the planets respond by expanding. As they lose mass to evaporation, their structure adjusts. Some models predict that planets like HAT P67b might actually shrink in the future if the rate of atmospheric loss exceeds the rate of stellar heating increase, though this is still debated, and there's a darker side to this story. For every HAT P67b we observe today, there might be dozens of planets that used to exist, but have since evaporated completely. We might be looking at a graveyard of former worlds where all that remains are the rocky cores, or perhaps nothing at all, the planets having been completely consumed by their stars. The hot Jupiters we see might be the survivors, the ones massive enough or distant enough to withstand the intense radiation, at least for now. What strikes me most about HAT P67b and WASP-17b is how they've expanded our conception of what a planet can be. Before we started finding exoplanets, we had this narrow view based on our solar system's 8 planets. But the universe doesn't limit itself to our imagination. It creates worlds in every configuration that physics allows, and sometimes in configurations we thought physics wouldn't allow. These bloated giants existing in states of slow disintegration, these backwards orbiting anomalies challenging our formation theories, they're nature's way of reminding us that the cosmos is far stranger and more diverse than we ever dreamed. But as extreme as these worlds are, they're still bound by the fundamental rules of gravity and orbits. There are other giants out there that challenge even those basic assumptions planets that formed in ways so different from our models that their very existence forces us to question what the word planet even means. Imagine a planet so far from its star that if you stood on its surface, hypothetically speaking, you'd need a telescope to see your sun as anything more than a bright point of light. A world orbiting 157 times farther from its star than Earth orbits ours so distant that its year lasts thousands of Earth years, floating in the cold darkness at the edge of its solar system. And yet this planet is absolutely enormous, 2.5 times the radius of Jupiter, 9 times its mass, a genuine giant, adrift in the cosmic void. But here's what breaks our understanding according to everything we know about how planets form, aurochs. 42BB shouldn't exist at all. Its distance from its star makes traditional planet formation impossible, which means it must have been born in a completely different way. Perhaps it didn't form like a planet at all. Perhaps it formed like a star. The year was 2013, and a team of astronomers led by Thane Curry was using the Subaru telescope in Hawaii and the Keck Observatory to study young star systems in the constellation Ophiuchus, about 460 light-years from Earth. They were employing a technique called direct imaging, which is exactly what it sounds like, actually photographing planets by blocking out the overwhelming light of their parent stars. This is incredibly difficult because a star is typically billions of times brighter than any planet orbiting it. It's like trying to photograph a firefly hovering next to a searchlight. The only planets we can directly image are young ones that are still hot from their formation, glowing in infrared light and located far enough from their stars that we can separate them optically. When Curry's team examined the young star Rox's 42b, they found something extraordinary. There, at an enormous distance from the star, was a bright infrared source, a planet glowing with the heat of its formation, even though that formation happened millions of years ago. When they calculated its properties from the infrared spectrum, the numbers were staggering. The planet designated Rox's 42b had a mass of approximately 9 times that of Jupiter. Its radius was estimated at about 2.5 Jupiter radii, making it one of the largest planets ever discovered, and its orbital distance approximately 157 astronomical units from its star. Let me give you some context for that distance. Neptune, the outermost planet in our solar system, orbits at about 30 AU from the Sun. The Kuiper Belt, that region of icy bodies beyond Neptune, where Pluto resides, extends to about 50 AU. Rox's 42b is 3 times farther out than even the Kuiper Belt. If you place this planet in our solar system at its current distance, it would be well into the scattered disk, that region, where objects have been gravitationally scattered into distant elongated orbits by interactions with Neptune. At that distance, the stellar radiation reaching Rox's 42b is minuscule. The star provides virtually no heat. If the planet has a surface temperature above absolute zero, it's because of internal heat, the residual warmth from its formation, and possibly ongoing radioactive decay in its core. This is a world living in permanent twilight. Its star, just another bright point among the constellations offering no meaningful warmth or light. Here's why this is a problem for planetary formation theory. In the standard model of planet formation, the one that explains Jupiter, Saturn, and the other gas giants in our solar system planets, build up through a process called core accretion. First, dust grains in the protoplanetary disk stick together through static electricity and gentle collisions, forming larger and larger clumps. These clumps become pebbles, then boulders, then kilometer-sized planetesimals. Eventually, one of these objects gets large enough that its gravity starts to dominate, and it begins sweeping up everything in its orbital path. Once the core reaches about 10 Earth masses, its gravity becomes strong enough to capture hydrogen and helium gas from the surrounding disk, and the object rapidly balloons into a gas giant. But this process requires time and material. At 157 AU from the star, several things make core accretion nearly impossible. First, the protoplanetary disk is much less dense out there. There's simply less material available to build a planet. Second, the orbital period is enormous. Rox 42b probably takes thousands of years to complete one orbit. At that distance, with such a long orbital period, objects move slowly relative to each other, which means collisions happen rarely and gently. Building up a 10 Earth mass core through slow, rare collisions is like trying to build a sandcastle with tweezers, theoretically possible, but practically implausible. Third, even if you did somehow build up a massive core, the protoplanetary disk only lasts a few million years before it's blown away by stellar winds and photoevaporation. There might not be enough time for a planet at that distance to grow to Jupiter size, let alone 9 Jupiter masses. So, if Rox's 42b didn't form through core accretion, how did it form? The leading alternative is called gravitational instability. In this scenario, the protoplanetary disk itself becomes gravitationally unstable. If a region of the disk is dense enough and cold enough, it can fragment directly into planet-sized clumps without going through the gradual accretion process. It's similar to how stars form from collapsing clouds of gas, just on a smaller scale. Think of it this way. Core accretion is like building a snowman by rolling a snowball around a yard, gradually picking up more snow. Gravitational instability is like a pile of snow on a roof suddenly collapsing all at once under its own weight. One is gradual and bottom up, the other is sudden and top down. If Rox's 42BB formed through gravitational instability, it would have come into existence much more like a star than like a traditional planet. The clump of gas would have collapsed under its own gravity, heating up in the center, as gravitational potential energy converted to thermal energy. For a few million years, the young Rox's 42BB would have been quite hot, glowing brightly in infrared, slowly cooling and contracting over time. This matches what we observe. Rox's 42BB is still warm from its formation, even though the star system is about 3 to 5 million years old. But here's where things get philosophically interesting. If Rox's 42BB formed like a star, is it really a planet? What's the difference between a very massive planet and a very small brown dwarf? This question isn't just semantic. It cuts to the heart of how we classify objects in the universe. The International Astronomical Union, the organization responsible for naming celestial objects and defining astronomical terms, has a working definition. If an object has a mass below 13 Jupiter masses and orbits a star, it's a planet. Above 13 Jupiter masses, if it's capable of fusing deuterium in its core, it's a brown dwarf. The 13 Jupiter mass threshold corresponds roughly to the minimum mass needed to sustain deuterium fusion, which is a kind of nuclear reaction that occurs at lower temperatures and pressures than the hydrogen fusion that powers normal stars. Rox's 42BB at 9 Jupiter masses falls safely below that threshold. It's officially classified as a planet, but it's uncomfortably close to the brown dwarf boundary, and it likely formed through the same process that creates small brown dwarfs. In many ways, it has more in common with failed stars than with planets like Jupiter, or even the hot Jupiters we've been discussing. This raises profound questions about planetary taxonomy. We've traditionally defined planets by their location objects that orbit stars. But if formation mechanism matters, then maybe Rox's 42BB represents a different class of object entirely. Some astronomers have proposed terms like planetary mass object or sub-brown dwarf to describe these ambiguous cases. The universe, as usual, doesn't care about our categories. It produces objects across a continuum of masses, compositions, and formation histories. And we're left trying to draw lines through that continuum to make sense of it all. Let me share a common misconception that trips people up. Many assume that mass and formation mechanism are linked, that all massive planets form one way and all small planets form another. But it's not that simple. We've found objects with planetary masses floating freely in space, not orbiting any star, that probably formed through gravitational instability. We've found brown dwarfs in tight orbits around stars that might have formed through core accretion. Mass formation mechanism and orbital configuration can all vary independently, creating a bewildering zoo of objects. What's particularly intriguing about Rox's 42BB is what it tells us about the diversity of planetary systems. In our solar system, the giant planets are at intermediate distances. Jupiter at 5 AU, Saturn at 10 AU, even Neptune at 30 AU is relatively close compared to Rox's 42BB's 157 AU orbit. We used to think our architecture was typical, but Rox's 42BB shows that planetary systems can have massive worlds at vast distances, structured in ways completely alien to what we see around our sun. And Rox's 42BB isn't alone. As direct imaging techniques have improved, we've found other massive planets in wide orbits. HR 8799 has 4 giant planets, the outermost, at about 68 AU. 1RXS 1609b orbits at about 330 AU from its star. These discoveries suggest that distant giant planets might be more common than we thought. We just hadn't been able to see them until recently, because they're so far from their stars and so faint. This has implications for our understanding of solar system architecture and planet migration. Some theories suggest that giant planets can form closer to their stars and then migrate outward through gravitational interactions with other planets or the protoplanetary disk. Could rocks 42b have formed closer in and been flung outward? The math gets complicated and the energies involved are enormous, but it's not impossible. Alternatively, maybe the disk around rocks 42b was unusually massive and extended, allowing for in situ formation at that great distance. There's also a temporal dimension to consider. Aurochs 42b is a young star system only a few million years old. The planets are still settling into their final configurations. It's possible that what we see now isn't the final architecture of the system. Over the next billion years, gravitational interactions might cause the planets to migrate orbits to shift, maybe even close encounters that eject worlds into interstellar space. We're seeing a snapshot of a system in its infancy, and we can only guess what it will look like when it matures. Here's something that keeps astronomers humble. We detected rocks 42b because it's young and hot, glowing brightly enough in infrared to be directly imaged despite its distance from the star. But if you took that exact same planet and aged it 4 billion years to the age of our solar system, it would cool down, stop glowing, and become essentially invisible to current telescopes. There could be dozens, hundreds, maybe thousands of rocks as 42b analogs in mature star systems that we simply cannot detect. Our census of distant giant planets is almost certainly incomplete, biased toward young systems, where the planets are still radiating their formation heat. The study of rocks 42b also teaches us about patience in science. This system was imaged in 2013, but confirming that the infrared source was actually bound to the star, and not just a background object, took years of follow-up observations. The planet moves so slowly in its orbit. Remember, it takes thousands of years to orbit. Once that, detecting its orbital motion requires watching it for many years. Only by confirming that it moves along with the star, sharing the same proper motion through space, could astronomers definitively prove it's a planet and not a distant, unrelated object. What strikes me most about rocks 42b is how it expands our conception of what planetary systems can look like. We found hot Jupiters orbiting their stars in days, and we were shocked. We found puffed-up giants with densities lower than balsa wood, and we were astonished. Now we find massive worlds orbiting in the frozen darkness, at distances where our theories said planets shouldn't exist, and we're forced to reconsider everything we thought we knew about planet formation. Each discovery doesn't just add to our catalog, it reshapes our understanding of how solar systems form and evolve. But rocks 42b's enormous mass raises another question, one that becomes more pressing the more planets we discover. When does a planet stop being a planet and become something else entirely? Where is the line between the largest planets and the smallest stars? And is there even a meaningful distinction to be drawn? There's an object floating in space right now that scientists have been arguing about for over a decade. Some call it the largest planet ever found. Others insist it's actually a failed star. The data shows it's about 21 times the mass of Jupiter, glowing faintly with internal heat, possibly burning deuterium in its core through nuclear fusion, yet orbiting a star like any planet would. Its name is GQ Loopy b, and depending on which astronomer you ask, it either belongs in the record books as a planetary giant or should be disqualified entirely from the category of planet. This isn't just academic nitpicking. This debate cuts to the fundamental question of what a planet actually is, and the answer is far messier than you might expect. If you're finding this deep dive into cosmic mysteries as fascinating as I do, a quick like would mean the world, and helps this video reach other space enthusiasts. And if you haven't subscribed yet, consider joining us for more journeys through the universe's most intriguing puzzles. The brown dwarf debate is one of the most contentious issues in modern astronomy, and it didn't start recently. Back in the 1960s, astrophysicist Shiv Kumar theorized that there should be objects that fall between planets and stars, objects massive enough to shine from gravitational contraction, but not massive enough to sustain hydrogen fusion. The nuclear reaction that powers normal stars, like our Sun. These hypothetical objects were dubbed brown dwarfs, though the name is somewhat misleading because they're not actually brown. They emit most of their light in the infrared spectrum, so if you could see them with your eyes, they'd probably look deep red or magenta. For decades, brown dwarfs remained theoretical. Astronomers searched for them, but found nothing. They became something of a cosmic joke, the missing link that maybe didn't exist. Then, in 1995, the same year, the first exoplanet around a sun-like star was confirmed. Astronomers finally discovered the first definitive brown dwarf, tied to 1, found in the Pleiades star cluster. Since then, we've found thousands of them, and each discovery has made the boundary between planets and brown dwarfs more blurred rather than clearer. The International Astronomical Union attempted to draw a bright line. They defined planets as objects with masses below 13 Jupiter masses, while anything above that threshold capable of deuterium fusion is a brown dwarf. Deuterium is a heavy isotope of hydrogen with 1 proton and 1 neutron in its nucleus, and it can fuse at much lower temperatures and pressures than regular hydrogen. The 13 Jupiter mass limit is approximately where deuterium fusion becomes possible, so it seems like a natural dividing line. But nature doesn't read our definitions. The reality is far more complicated. Let's examine GQ Loopy b more closely. Discovered in 2005 orbiting the young star GQ Loopy in the constellation Lupus, this object immediately sparked controversy. Initial measurements suggested a mass somewhere between 1 and 36 Jupiter masses. That's an enormous uncertainty range, basically saying, we know something's there, but we're not sure what it is. Later refinements narrowed the estimate to around 10 to 36 Jupiter masses, which still spans the planet-brown dwarf boundary. The radius measurements were even more problematic. Different studies using different methods produce values ranging from 1.8 to 4. 6 Jupiter radii, with some measurements carrying error bars so large they made the result almost meaningless. One analysis suggested the radius could be as large as 6 Jupiter radii, which would make it absolutely enormous, potentially the largest known planetary mass object. But the uncertainty was so high that you couldn't say anything definitive. Why is it so hard to measure GQ Loopy b is young, probably only about 1 to 5 million years old? And young objects are still contracting and cooling. Their properties change over time. Additionally, the system is about 500 light-years away, which makes precise measurements difficult. The object is faint, sitting right next to a much brighter star, and separating their light cleanly is technically challenging. But the mass uncertainty is the real killer. If GQ Loopy b is on the low end of the mass, estimates around 10 Jupiter masses, it's definitely a planet. If it's on the high end, around 36 Jupiter masses, it's definitely a brown dwarf. We don't know which it is, and without a precise mass, we can't classify it. This raises an interesting philosophical question. Does the classification of an object depend on our ability to measure it? If we had perfect instruments that could determine GQ Loopy b's mass to within 0.1%, would that change what it fundamentally is? Obviously not the object itself, doesn't care what we call it. But our catalogs, our databases, our understanding of planetary demographics all depend on being able to draw these distinctions. Now, let's consider another controversial object. DH Tauri b discovered orbiting a young star in the Taurus star-forming region. This one has an estimated mass of about 12 Jupiter masses right on the boundary and a radius of approximately 1.7 to 2.1 Jupiter radii. Unlike GQ Loopy b, the measurements for DH Tari b are relatively precise. The problem is that at 12 Jupiter masses, we don't know if it's fusing deuterium or not. Here's the thing about deuterium fusion. It's not an on-off switch. It doesn't suddenly turn on at exactly 13 Jupiter masses. The threshold depends on the object's composition, how much hydrogen versus helium it contains, the presence of heavier elements, even its age and thermal history. An object with more metals might start deuterium fusion at a slightly lower mass. An object that's very young and still contracting might not have reached the core temperatures needed for fusion, even if it has the mass. So, DH Tauri b might be burning deuterium, or it might not be. We can't tell from current observations. Does that make it a planet or a brown dwarf? The honest answer is, we don't know, and the question might not even be meaningful. PDS 70b presents a different challenge. This object, discovered in 2018, orbits the star PDS 70 at a distance of about 20 AU and is remarkable because we can actually see it carving out a gap in the protoplanetary disk around its star. It's a planet caught in the act of formation, sweeping up material as it grows. Measurements suggest a mass between 2 and 17 Jupiter masses, again straddling the boundary, and a radius of about 2 to 2.8 Jupiter radii, making it potentially one of the largest planets by radius. But is PDS 70b finished forming? It's embedded in a disk of gas and dust, actively accreting material. Its current mass is less than its final mass will be. If it ends up above 13 Jupiter masses after it's done, growing, was it a planet that became a brown dwarf? Can objects change categories over time? These aren't just abstract questions. How we classify objects affects how we count them statistically. If we're trying to determine what percentage of stars have giant planets versus what percentage have brown dwarf companions, misclassifying even a small number of objects can skew the statistics significantly. And those statistics inform our theories of formation. Whether we think these objects formed like planets through core accretion or like stars through gravitational instability. There's another complication: free-floating planetary mass objects. We've discovered hundreds of objects with planetary masses, some as low as a few Jupiter masses that don't orbit any star. They're drifting freely through interstellar space, possibly ejected from planetary systems through gravitational interactions, or possibly formed in isolation through the collapse of small gas clouds. Do we call these planets, even though they don't orbit stars? The IAU's definition says no. A planet must orbit a star. But if a Jupiter mass object formed through core accretion in a protoplanetary disk and was then ejected, did it stop being a planet the moment it left the system? That seems absurd. Some astronomers have proposed we should classify objects by formation mechanism rather than mass. Objects that formed through core accretion are planets regardless of mass. Objects that formed through gravitational instability or cloud collapse are brown dwarfs or sub-brown dwarfs regardless of mass. This has a certain logical appeal. It groups objects by their origin rather than their current properties. But it's also completely impractical because we can't observe formation mechanisms directly. We can only infer them from properties like mass composition and orbital characteristics, and those inferences are often uncertain. Let me give you a concrete example of how messy this gets. In 2004, astronomers discovered 2M1207b, an object with about 4 to 5 Jupiter masses orbiting the brown dwarf 2M1207 at a distance of about 40 AU. Is 2M1207b a planet by mass? Yes. But it's orbiting a brown dwarf, not a star. The IAU's definition requires planets to orbit stars. So, technically, 2M1207b is not a planet by the official definition, even though it would be if its host were just slightly more massive and qualified as a red dwarf star instead of a brown dwarf. The absurdity of this situation should be apparent. Whether 2M1207b counts as a planet depends on the nuclear fusion status of the object it orbits, which has nothing to do with 2M1207b's own properties. It's like saying whether you're human depends on whether your parents are exactly 5 feet tall or not. It makes no sense. Here's a common mistake people make when thinking about this problem, assuming that precise definitions are essential for doing science. They're not. Biology doesn't have a universally agreed upon definition of species, and yet biologists manage to do rigorous work studying evolution and ecology. Geologists argue about the exact definition of mineral, but mineralogy proceeds just fine. In astronomy, we can study the properties, formation, and evolution of objects without needing to agree on whether they're planets or brown dwarfs, as long as we're clear about what we're measuring. What matters is not the label, but the physics. An object with 12 Jupiter masses behaves a certain way. It has a certain luminosity, a certain cooling rate, a certain ability to retain an atmosphere. Those properties don't change based on what we decide to call it. The taxonomy is for our convenience, not nature's. That said, there is value in having working definitions, even imperfect ones, because they facilitate communication. When I say brown dwarf, you should have some idea what I'm talking about, even if the boundaries are fuzzy. The key is to remember that these are human constructs imposed on a continuous spectrum of objects. The brown dwarf debate also teaches us humility. In 2006, when the IAU famously demoted Pluto from planet status, there was public outcry. People felt attached to the 9-planet solar system they had learned about in school, but the decision was driven by the discovery of Eris, an object beyond Neptune that's more massive than Pluto, and the realization that there are probably thousands of similar objects in the Kuiper Belt. Either we had to call all of them planets, which would make the term nearly meaningless, or we had to draw a line somewhere. The IAU chose to draw that line based on clearing the neighborhood. Planets must be the dominant gravitational body in their orbital zone. By that definition, Pluto doesn't qualify because it shares the Kuiper Belt with countless other objects. The brown dwarf situation is similar. We're discovering objects across a continuum of masses from 1 Jupiter mass up to the hydrogen burning limit at about 75 to 80 Jupiter masses. Drawing a line at 13 Jupiter masses is somewhat arbitrary based on a physical process that doesn't turn on sharply at that mass. But we need some working definition to organize our catalogs and discuss patterns in the data. What's fascinating is how the debate has evolved our understanding. 20 years ago, we thought planets and brown dwarfs were clearly distinct populations. Now, we know there's a continuous distribution of masses, a range of formation mechanisms, and complex evolutionary paths that can blur any simple classification. The universe is more nuanced than our categories, and that's not a problem, it's a feature. It means there's always more to discover, more to understand, more complexity to unravel. And this brings us to an even deeper question. If mass doesn't cleanly separate planets from brown dwarfs, and if formation mechanism is difficult to determine observationally, what other properties might help us understand these objects? One crucial property we haven't fully explored yet is density, the relationship between an object's mass and its size. Because here's a surprising fact. Adding more mass to a planet doesn't always make it bigger. In fact, beyond a certain point, adding mass actually makes planets smaller. This counterintuitive physics governs the maximum size any planet can reach, and it's the key to understanding why even the most inflated hot Jupiters have limits to their expansion. Here's a puzzle that seems to violate common sense. If you took Jupiter and somehow added another Jupiter's worth of mass to it, the resulting object wouldn't be twice as big. In fact, it would barely be any bigger at all. Add 10 Jupiters worth of mass, and the object would actually be smaller than the original Jupiter. Keep adding mass, and eventually you'd have something that weighs as much as 80 Jupiters, but is only about 70% of Jupiter's size. This seems impossible. How can adding more material make something shrink? But it's not magic, it's physics. And understanding this paradox is the key to understanding why there's a maximum size that planets can reach, no matter how much mass they accumulate. The story of this discovery begins not with exoplanets, but with a brilliant Indian physicist named Subramanian Chandrasekhar. In 1930, while traveling by ship from India to England to begin his graduate studies at Cambridge, the 19-year-old Chandrasekhar worked out the mathematics of what happens to stars when they die. He discovered that when a star runs out of fuel and can no longer support itself against gravity through nuclear fusion, it collapses into what we now call a white dwarf, an incredibly dense object where gravity has compressed the matter so tightly that electrons are squeezed as close together as quantum mechanics allows. But Chandrasekhar discovered something even more profound. There's a maximum mass for white dwarfs about 1.4 times the mass of our Sun. If a dying star's core is more massive than this, limit gravity will overwhelm even the quantum pressure of electrons, and the star will collapse further into a neutron star or black hole. This limit, now called the Chandrasekhar limit, earned him the Nobel Prize in Physics in 1983. The physics behind the Chandrasekhar limit involves something called electron degeneracy pressure. In normal matter, electrons orbit atomic nuclei with plenty of space between them. But when you compress matter to extreme densities, the electrons get pushed so close together that quantum mechanics steps in. The Pauli exclusion principle, one of the fundamental rules of quantum physics, states that no two electrons can occupy the exact same quantum state. When electrons are squeezed into a small volume, they're forced into higher and higher energy states, creating a pressure that resists further compression. This same physics applies to planets, particularly gas giants like Jupiter, and it creates the counterintuitive result that adding mass to a gas giant doesn't necessarily make it bigger. Let me walk you through the physics step by step. When you have a ball of hydrogen and helium held together by gravity, which is what a gas giant is, there's a balance between gravity trying to squeeze everything together and internal pressure pushing outward. For a relatively low-mass planet like Jupiter, most of that internal pressure comes from thermal motion. The hydrogen and helium atoms are moving around rapidly, and that motion creates pressure just like air molecules bouncing around create pressure in a balloon. As you add more mass, gravity gets stronger, squeezing the planet more tightly. This compression heats the interior. Remember, compression always generates heat, which increases the thermal pressure. But it also increases the density. And here's where things get interesting. As the density increases, the electrons start to get pushed closer together, and quantum mechanics starts to matter. For objects with masses around Jupiter's mass, or higher electron, degeneracy pressure begins to contribute significantly to the total pressure supporting the planet against gravity. And unlike thermal pressure, which increases with temperature, degeneracy pressure depends only on density. It's a purely quantum mechanical effect that doesn't care how hot or cold the material is. This leads to a remarkable consequence. As you add more mass to a gas, giant gravity compresses it more, which increases the density, which increases the degeneracy pressure, which allows the planet to resist gravity at a smaller radius. The added mass doesn't expand the planet, it compresses it. The planet shrinks even as it gets more massive. Now, this doesn't happen indefinitely. There's a sweet spot where planets reach their maximum size. For gas giants composed primarily of hydrogen and helium, this maximum occurs at roughly 1 to 3 Jupiter masses, depending on the planet's age, temperature, and exact composition. At this mass range, thermal pressure and degeneracy pressure are balanced in such a way that planets achieve their largest possible radii, typically between 1 and 2 Jupiter radii. Beyond about 3 Jupiter masses, degeneracy pressure increasingly dominates and planets start to shrink as you add more mass. By the time you reach 10 to 15 Jupiter masses, the planet-brown dwarf boundary, the object might have a radius of only 0.9 to 1.0 Jupiter radii. despite being 10 times more massive. And if you continue adding mass all the way up to the brown dwarf and stellar regime, the radius continues to decrease. A brown dwarf with 50 Jupiter masses might have a radius of only 0.8 Jupiter radii. Even the smallest red dwarf stars, which have about 80 Jupiter masses, have radii only slightly larger than Jupiter, despite being vastly more massive. This creates what astronomers call the mass-radius relationship for gas giants, and it's one of the most important tools for understanding these objects. When you plot the mass versus radius for all known gas giants, you see a clear pattern. Radius increases with mass up to about 1 to 3 Jupiter masses, then stays roughly constant, or even decreases as mass continues to increase. But here's where it gets complicated. Hot Jupiters don't follow this relationship. Planets like HAT P67b and WASP-17b have radii much larger than the standard mass-radius relationship predicts. They're inflated beyond what degeneracy pressure alone can explain. This is the radius anomaly we discussed earlier. The intense heating from their nearby stars is doing something. We're still not entirely sure what counteracts the compressive force of gravity and degeneracy pressure, keeping these planets puffed up to enormous sizes. Think of it this way. The standard mass-radius relationship is like a curve describing how big different masses of clay would compact under their own weight. Cooler gas giants like Jupiter follow that curve fairly well. But hot Jupiters are like clay that's been placed in an oven. The heat makes them expand, pushing them above the curve. The hotter they are, the more they deviate from the standard relationship. This has profound implications for what counts as the biggest planet. If we're measuring by mass, the largest planets are those right at the brown dwarf boundary, around 13 Jupiter masses. But if we're measuring by radius, the largest planets are the most inflated hot Jupiters with masses of only 1 to 3 Jupiter masses. These are completely different objects. It also means there's a fundamental limit to how large a planet can be. No matter how much you heat a gas giant, no matter how much stellar radiation you pump into its atmosphere, you can't inflate it arbitrarily large. There's a maximum radius of roughly 2 to 2.5 Jupiter radii, beyond which the planet would simply not be gravitationally bound. It would evaporate into space faster than it could hold itself together. This is why astronomers get excited when they find planets like HAT P67b pushing right up against this theoretical limit. These are objects at the extreme edge of what's physically possible. They're being heated so intensely that they're on the verge of disintegration, held together by the barest margin of gravitational force. Push them just a little harder, and they'd cease to be planets at all. Let me give you a common misconception that trips people up. Many assume that density is a good indicator of composition, that low-density planets must be made of light materials, and high-density planets must be made of heavy materials. This is partly true, but oversimplified. A gas giant made entirely of hydrogen and helium can have a wide range of densities depending on its mass and temperature. Jupiter has a density of 1.3 grams per cubic centimeter. Saturn, also made primarily of hydrogen, and helium, has a density of 0.7 grams per cubic centimeter. HAT P67b, also hydrogen and helium, has a density around 0.05 grams per cubic centimeter. Same composition, wildly different densities, all because of differences in mass and internal temperature. Conversely, you can't necessarily determine a planet's mass from its density unless you also know its size. A large, low-density planet might have the same mass as a small, high-density planet. This is why measuring both mass and radius is so important. You need both to understand the object's structure and composition. The mass-radius relationship also has implications for planetary interiors. Jupiter, for example, is thought to have a small rocky core of perhaps 10 to 20 Earth masses surrounded by a thick envelope of hydrogen and helium. But at the pressures inside Jupiter, millions of atmospheres, hydrogen doesn't behave like a gas anymore. In the outer layers, it's a molecular fluid. Deeper down, under increasing pressure, the hydrogen molecules break apart, and the electrons are stripped away, creating what's called metallic hydrogen, a form of hydrogen that conducts electricity like a metal. For more massive gas giants approaching the brown dwarf boundary, the core may be compressed to even more exotic states. The pressures in the center can exceed those at the core of the Sun, creating conditions where hydrogen itself undergoes phase transitions into forms we can't reproduce in any laboratory on Earth. These aren't just theoretical curiosities. The properties of matter under these extreme conditions affect the planet's cooling rate, its magnetic field generation, and its long-term evolution. There's also a temporal dimension to the Moss-radius relationship. Young planets freshly formed and still hot from gravitational contraction are larger and less dense than old cooled planets of the same mass. Jupiter itself was probably 10 to 20% larger when it formed 4.5 billion years ago. Over time, as it radiated away its internal heat, it contracted to its current size. This process is incredibly slow. Planets cool over billions of years, but it means the mass-radius relationship is age-dependent. A young, hot Jupiter mass planet might have a radius of 1.3 Jupiter radii, while an old, cold Jupiter mass planet might have a radius of only 0.95 Jupiter radii. This creates challenges for understanding exoplanets, especially those around young stars. When we measure a planet's radius, we're seeing a snapshot of its current state, which depends on its age, heating history, and formation conditions. Two planets with identical masses and compositions might have different radii simply because one is younger than the other. Astronomers have developed sophisticated models to account for these effects. By combining observations of mass and radius with estimates of the star's age and measurements of the planet's atmospheric temperature, they can work backwards to infer the planet's composition, the size of its rocky core, and its thermal evolution history. These models have revealed that giant planets are remarkably diverse in their interior structures, even when they have similar masses. Here's something that still amazes me. We're inferring the properties of matter under conditions that don't exist anywhere in our solar system, based on measurements of objects over 1,000 light-years away. We measure how much starlight a planet blocks during a transit. Combine that with measurements of how much the star wobbles. And from those two numbers alone, we can deduce what's happening in the planet's core, where pressures exceed anything we can create in a laboratory. That's the power of physics. The same equations that describe how gases compress on Earth also describe how they compress inside a distant gas giant, and those equations let us see the unseeable. What's particularly elegant about the density paradox is how it reveals the self-limiting nature of planet formation. There's a maximum size planets can reach, not because they can't gather more mass, but because gathering more mass makes them denser rather than bigger. This natural limit exists independently of any particular formation, scenario, or environmental condition. Whether a planet forms through core accretion or gravitational instability, whether it migrates inward or stays put, whether it's roasted by its star or frozen in darkness, it cannot exceed roughly 2 Jupiter radii without losing gravitational binding. Physics itself enforces this boundary. And yet, as with everything we've discussed, there are exceptions and edge cases. Some theoretical models suggest that under very specific conditions, perhaps a planet with an unusually large rocky core and an atmosphere of hydrogen heated to thousands of degrees, you might get radii slightly exceeding the 2 Jupiter radii limit. We haven't found such an object yet, but absence of evidence isn't evidence of absence. The universe has surprised us before. This brings us to a crucial realization. Our search for the largest planet has been constrained by what we've been able to observe. We've found inflated hot Jupiters because they're relatively easy to detect. They're big, they transit their stars frequently, and they're bright in infrared. But there's a whole population of planets we've barely begun to explore, planets in conditions and configurations we haven't systematically searched. What giant worlds might still be waiting to be discovered? hidden in the observational blind spots of our current technology. Right now, as you listen to this, there are planets out there, perhaps dozens, perhaps hundreds, that are larger than anything we've discovered so far. They're orbiting stars. We can see with telescopes. They're massive enough to be detected with current technology, but we haven't found them yet. Not because they don't exist, but because we haven't been looking in the right places at the right times or with the right methods. Our catalog of exoplanets isn't a complete census of what's out there. It's more like the highlights reel, showing us the easiest discoveries while the majority of worlds remain hidden in observational shadows. The question isn't whether larger planets exist, it's where they're hiding and what we need to do to find them. The story of what we're missing begins with understanding observational bias. Every planet detection method has blind spots, regions of parameter space where planets could exist, but our instruments can't see them. The transit method, which has discovered the majority of known exoplanets thanks to missions like Kepler and TESS, has several significant biases built into how it works. First, geometry bias. Remember that we can only detect transits when a planet's orbital plane is aligned edge-on from our perspective. For a planet orbiting at Earth's distance from a sun-like star, the probability that we happen to be viewing the system at the right angle is about 5%. That's 1 in 200. For planets in wider orbits, the probability drops even further. A Jupiter-like planet orbiting at 5 AU has only about a 0.1% chance of transiting from our viewpoint. This means we're missing the vast majority of planets simply because of bad luck in viewing geometry. Second, duration bias. Transits only happen once per orbital period. If a planet orbits its star every 100 days, we see one transit every 100 days. For planets in Jupiter-like or wider orbits, the orbital periods are measured in years or even decades. The Kepler mission operated for about 4 years of high-quality data collection. It could reliably detect planets with orbital periods up to about 1 or 2 years, but anything with a longer period would transit only once or twice during the mission, making confirmation difficult. TESS, the current premier transit hunting mission, monitors each patch of sky for only 27 days in most areas, which means it's primarily sensitive to planets with very short orbital periods, the hot Jupiters and super-Earths, that orbit in days or weeks, not months or years. This creates a massive blind spot in our surveys. We've found thousands of planets in tight orbits close to their stars, but planets in wider orbits, even if they're enormous, remain largely undiscovered. There could be inflated giants orbiting in the habitable zones of their stars, where temperatures are moderate and stellar heating is less extreme. These planets might have radii of 2 or even 3 Jupiter radii puffed up by different heating mechanisms than the roasted hot Jupiters we know. But if they orbit once every year, or 2 current transit surveys would miss them. Third, there's host star bias. The transit method works best for small, dim stars because planets block a larger fraction of a small star's light. A Jupiter-sized planet transiting a red dwarf might block 2 to 3% of the star's light, creating a clear, easily detectable signal. The same planet transiting a massive bright star might block only 0.5% of the light, requiring much more precise photometry to detect. As a result, our surveys are biased toward planets around small stars and have systematically undersampled planets around large stars. But here's what's interesting: massive stars tend to have more massive planets. Theoretical models and limited observations suggest that the likelihood of forming giant planets increases with stellar mass, probably because more massive stars have more massive protoplanetary disks, with more material to build planets. So, we might be missing a population of especially large gas giants around massive stars simply because they're harder to detect. The radial velocity method, which detects planets by measuring the wobble they induce in their star's motion, has its own set of biases. It's most sensitive to massive planets in close orbits because these create the largest wobbles. A Jupiter-mass planet orbiting in 4 days creates a much larger radial velocity signal than a Jupiter-mass planet orbiting in 4 years. The method can detect long-period planets, but it requires monitoring the star for multiple orbital periods to confirm the detection. For a planet with a 20-year orbit, you need decades of observations before you can be confident you've detected a real planet, rather than some other stellar variability. This means we've barely scratched the surface of giant planets in wide orbits. The planets we have discovered in Jupiter-like orbits around 5 AU from their stars number only in the dozens compared to the thousands of hot Jupiters we've found. And for planets at even greater distances, the sample size drops to just a handful. We know these planets must be common because our own solar system has Jupiter and Saturn in wide orbits. And there's no reason to think we're unique. But finding them requires patience and long baseline observations that we're only now beginning to accumulate. Direct imaging, the method that discovered Aurochs, 42BB, and other distant giants, has its own limitations. It can only detect young hot planets that are still glowing from their formation heat, and even then, only if they're far from their host stars, where the stellar glare doesn't overwhelm them. Older planets that have cooled down become essentially invisible to current direct imaging instruments. There could be fully mature gas giants the size of HAT P67b, orbiting at moderate distances from mature stars, and we'd have no way to detect them with current technology. Then there's the super-Earth problem, which isn't directly about finding the largest planets, but reveals something important about our observational capabilities. Super-Earths are planets with masses between Earth and Neptune, roughly 1 to 10 Earth masses. They're incredibly common in other star systems. In fact, they might be the most common type of planet in the galaxy. But our solar system doesn't have any. The closest thing we have is Uranus and Neptune at 14 and 17 Earth masses respectively, which are actually mini-Neptunes rather than super-Earths. Why don't we have super-Earths? It's not that they couldn't form here. The leading theory is that Jupiter's migration through the inner solar system billions of years ago disrupted planet formation and prevented super-Earths from assembling. But the point is that our own solar system is not a representative sample of planetary systems. It's a single example, possibly unusual in some ways, and we can't extrapolate from it to the full diversity of planets in the galaxy. There are whole categories of planets we simply didn't know existed until we started finding exoplanets. This brings us to an exciting frontier. What types of giant planets might exist that we haven't discovered yet? Let me walk you through some possibilities based on theoretical models and the gaps in our current observations. First, there could be inflated giants around evolved stars. As stars age and begin to swell into red giants, they become much brighter, pumping increased radiation into any orbiting planets. A planet that was a normal Jupiter-sized gas giant during the star's main sequence lifetime might inflate dramatically as the star evolves. Some models predict radii as large as 3 to 4 Jupiter radii for planets around bright subgiant and red giant stars. We've found a few planets around evolved stars, but the sample size is tiny, partly because these stars are often too bright and variable for precise transit photometry. There could be a whole population of extreme inflated giants around aging stars waiting to be discovered. Second, there might be giants with unusual compositions. Most gas giants are primarily hydrogen and helium because those are the most abundant elements in the universe. But what if a planet formed in a region of the protoplanetary disk, enriched in heavier elements? Theoretical models suggest that planets with higher metallicity, more carbon, oxygen, nitrogen, and other heavy elements mixed into their hydrogen-helium envelopes might behave differently. They could have enhanced opacity in their atmospheres, trapping more heat and potentially inflating to larger sizes. Or they could have denser interiors that allow them to remain more compact despite having significant mass. We don't know because we haven't found enough examples to test these theories. Third, consider planets around binary stars. About half of all sun-like stars are in binary or multiple star systems. Yet our planet surveys have historically avoided these systems because they're more complicated to analyze. A planet in a binary system could receive radiation from two stars, potentially heating it more than a similar planet around a single star. Or it could have an unusual orbital configuration that affects its tidal heating and evolution. We've started finding planets in binary systems in recent years, the famous circumbinary planets that orbit both stars, like Tatooine in Star Wars, but the sample size is still small. Fourth, there's the question of planets around very young stars. We've found a few like PDS 70b, but young star systems are often surrounded by thick disks of gas and dust that obscure our view of the planets. These dusty disks make transit detections difficult and complicate direct imaging. Yet young planets are potentially the largest. They're still hot and bloated from formation. They haven't had time to contract and cool. There might be planets out there right now, with radii of 3 or even 4 Jupiter radii, but they're hidden behind veils of circumstellar material that won't dissipate for another few million years. The upcoming generation of telescopes and instruments promises to fill in some of these gaps. The James Webb Space Telescope, launched in 2021, has infrared capabilities that allow it to study exoplanet atmospheres in unprecedented detail and directly image giant planets that would be invisible to earlier instruments. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will use gravitational microlensing to find planets across a wide range of orbital distances, including cold giants far from their stars. Ground-based, extremely large telescopes currently under construction. The 30-meter telescope, the Giant Magellan Telescope, and the European. Extremely large telescope will have the resolution and sensitivity to directly image planets that are currently beyond our reach. These instruments will also help us understand the planets we've already found. For inflated giants like HAT P67b, spectroscopic observations with JWST can reveal the detailed composition of their atmospheres, measure temperature profiles at different altitudes, and potentially detect atmospheric escape in real time. These observations will test our theories about what causes radius inflation and help us predict which planets should be the most inflated. There's also the statistical approach. As our exoplanet catalog grows, we can use statistical methods to infer the properties of planets we haven't directly detected. If we know the detection efficiency of our instruments as a function of planet size, mass, and orbital period, we can work backwards to estimate the true occurrence rates of different planet types. These studies suggest that for every hot Jupiter, we've found there are probably 10 or more giant planets in wider orbits that we've missed. The biggest planet ever discovered might not be the biggest planet that exists. It's just the biggest we've been lucky enough to find so far. Here's a humbling thought. The first exoplanet around a sun-like star was discovered in 1995. It's been less than 30 years. In that time, we've gone from knowing 0 exoplanets to knowing over 5,000. Our detection methods have improved dramatically. Our theoretical understanding has deepened. But we're still in the early stages of this field. Future astronomers looking back at our era will probably see obvious gaps in our understanding, blind spots we didn't even realize we had. The catalog of planets we're building now is like a rough sketch. It captures the basic outlines, but the details and nuances are still being filled in. What excites me most is the possibility of finding something completely unexpected. Every major advance in exoplanet detection has revealed planets we didn't predict. Hot Jupiters weren't expected based on solar system architecture. Super Earths weren't expected because we don't have them. Inflated giants weren't expected because the physics wasn't well understood. Each time we've looked at the universe with new instruments or new techniques, nature has surprised us. What surprises are waiting in the data we'll collect over the next decade? What bizarre, physics-defying, theory-challenging planets are out there waiting to be discovered? And this leads us to the final question in our journey. What does all this tell us? After exploring the biggest planets we've found, the physics that governs their sizes, the boundaries between planets and stars, and the vast populations of worlds still waiting to be discovered, what have we learned about our place in the universe and the cosmic process that creates planetary systems? So here we are at the end of our journey through the realm of planetary giants. We've met worlds that defy physics, planets that shouldn't exist, but do objects that blur the line between planet and star, and we've glimpsed the vast populations of undiscovered worlds still hidden in the darkness. But what does it all mean? After cataloging the biggest, the strangest, the most extreme planets in the cosmos, what have we actually learned? The answer, I think, goes far deeper than just knowing which planet holds the size record. It's about understanding our own origins, recognizing the extraordinary diversity of planetary systems, and fundamentally redefining what we thought was possible in the universe. Let me start with a question that might seem simple, but opens into profound territory. Why do we care about finding the biggest planet? Is it just record-keeping, cosmic bookkeeping, the astronomical equivalent of tracking who holds the world record for the tallest building or the fastest marathon? I'd argue it's something much more meaningful. Every extreme object we discover, the hottest, the coldest, the largest, the densest, teaches us about the boundaries of what's physically possible. These outliers stress test our theories, revealing whether our understanding of physics is robust enough to explain not just the average case, but the edge cases where conditions are pushed to their limits. TARES 4b, with its balsa wood density, forced us to rethink atmospheric physics on hot Jupiters. Before its discovery, our models predicted that planets couldn't be that inflated. Its existence proved our models were incomplete, missing some crucial heating mechanism. That sent theorists back to their computers, and over the following decade, they developed more sophisticated models of atmospheric circulation, tidal heating, and radiative transfer. Now, our theoretical understanding is much more complete, not just for inflated hot Jupiters, but for gas giant atmospheres in general. HAT P67b and WASP 17b push those boundaries even further, showing us that planets can exist in states of slow disintegration, shedding mass into space, while being baked by stellar radiation intense enough to ionize their atmospheres. These aren't stable configurations that will last billions of years. They're transient states in planetary evolution. We're witnessing these planets during a relatively brief phase of their lives, which raises fascinating questions about planetary demographics. How many planets have already evaporated completely? How many will suffer the same fate in the future? What fraction of the planets we see around other stars are doomed to eventual destruction? Aurochs. 42BB taught us that planet formation is more versatile than we imagined. For decades, we built our theories around core accretion because that's how Jupiter formed. Finding massive planets at enormous orbital distances where core accretion is too slow forced us to seriously consider gravitational instability as an alternative formation mechanism. Now, we understand that nature has multiple pathways to create giant planets, and which pathway dominates depends on the local conditions in the protoplanetary disk. This has implications beyond just explaining Aurochs, 42BB. It helps us understand the full spectrum of planetary systems, from compact systems with multiple hot Jupiters to wide systems with distant giants to systems like our own, with planets at intermediate distances. The brown dwarf debate, frustrating as it is when you're trying to classify objects, cleanly reveals something beautiful about nature. The universe doesn't care about our taxonomies. There's a continuum of objects from rocky planets to gas giants to brown dwarfs to red dwarf stars, each blending smoothly into the next. The boundaries we draw are for our convenience, not because nature has clean separations. This is actually a profound lesson that applies far beyond astronomy. In biology, we struggle to define species because organisms exist on a continuum of genetic similarity. In geology, we debate whether certain formations are mountains or hills. Categories are human constructs, and the universe is under no obligation to fit neatly into them. The density paradox, the fact that adding mass to a gas giant makes it smaller rather than larger, is perhaps my favorite example of counterintuitive physics. It's a direct consequence of quantum mechanics, the strange rules that govern the subatomic world manifesting at planetary scales. Quantum effects, which we usually associate with tiny particles and microscopic phenomena, are actually crucial for understanding objects thousands of times more massive than Earth. This is the beauty of physics. The same fundamental laws apply everywhere, from the smallest quarks to the largest galaxies. Understanding electron degeneracy pressure in white dwarfs helps us understand the internal structure of Jupiter, which helps us understand why there's a maximum size for gas giants, which helps us interpret observations of exoplanets. It's all connected. What strikes me most profoundly is the sheer diversity of planetary systems. Before 1995, our sample size was 1, our solar system. We had 8 planets, well 9 at the time, arranged in a particular configuration, and it was natural to assume this was typical. Rocky planets close to the sun, gas giants farther out, small icy bodies at the edge. That's just how solar systems work, right, wrong. So, completely, utterly wrong. The exoplanet revolution revealed that our solar system is just one possibility among countless variations. There are systems where massive planets orbit in days, systems where planets orbit backwards, systems with planets so close to their stars they're being vaporized, systems with giant planets in the habitable zone where Earth-like temperatures prevail, systems with planets at distances where our models say formation is impossible, systems with 5, 6, 7 giant planets all packed into orbits closer than Mercury. Every configuration that doesn't violate fundamental physics seems to exist somewhere. And here's the kicker, we might actually be unusual. Some studies suggest that solar systems like ours with small rocky planets in the inner system and gas giants in the outer system, with relatively circular orbits and long-term stability, might be less common than we initially thought. The chaotic systems with migrating giants' close encounters and planets flung into interstellar space might be the norm, and we're the exception that survived with our orderly architecture intact. This has implications for questions about the prevalence of habitable worlds and the likelihood of life elsewhere in the universe. Think about what our journey through giant planets has revealed about planetary formation and evolution. Planets don't just form and stay put. They migrate through their systems driven by interactions with the gas disk, with other planets, with their host stars. They can move inward, becoming hot Jupiters roasted by stellar radiation. They can move outward, becoming cold giants in the frozen darkness. They can collide, merge, be ejected into interstellar space. Planetary systems are dynamic, evolving over billions of years, and what we see today is just a snapshot of an ongoing process. This dynamism means that predicting a system's final configuration from its initial conditions is incredibly difficult. It's like weather forecasting, but on timescales of millions of years. Small changes in initial conditions, a slightly different disk mass, here a slightly different migration rate. There can lead to radically different outcomes. One system produces a hot Jupiter, another produces a cold giant, a third produces no giant planets at all. The same physics, different outcomes, because planetary formation is a chaotic process sensitive to initial conditions. What does this tell us about our own origins? If planetary systems are so diverse and our configuration is possibly unusual, what does that mean for Earth? One interpretation is that we're cosmically lucky. Jupiter's migration through the early solar system could have disrupted the formation of Earth and the other inner planets. Instead, Jupiter migrated inward to about 1.5 AU, then reversed course and migrated back outward, leaving the inner system relatively undisturbed. This grand tack hypothesis is still debated, but it suggests that small changes in Jupiter's migration history could have prevented Earth from forming at all. Alternatively, maybe systems like ours are more common than we think, but they're harder to detect. The observational biases we discussed mean we're better at finding weird systems than normal ones. In another decade, as our detection methods improve and we survey more stars, we might find that solar system analogs are actually quite common. We don't know yet, and that uncertainty is part of what makes this field exciting. Let me share something personal. When I first learned about exoplanets as a student, I was captivated by the simple fact that planets exist around other stars. It seems obvious now, but for most of human history, we didn't know that for certain. We theorized, we speculated, but we didn't know. And then we found them, and the universe revealed itself to be far stranger and more diverse than our theories predicted. That sense of discovery of the universe surprising us with its creativity is what drives many of us in this field. Every new planet is a reminder that nature's imagination exceeds our own. The biggest planet ever discovered, whether it's HAT P67b or Rox's 42BB, or some object we haven't found yet, is not just a record holder. It's a window into planetary physics at its most extreme. It's a test case for our theories. It's an example of what's possible when you take the basic ingredients of hydrogen, helium, and gravity and arrange them under just the right conditions. And it's a reminder that in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, each potentially hosting multiple planets, the diversity of worlds out there is beyond our ability to fully catalog or comprehend. What would it be like to stand on one of these giant planets? Well, you couldn't. Of course, they're balls of gas with no solid surface. But imagine floating in the upper atmosphere of HAT P67b, suspended in hydrogen gas, heated to thousands of degrees, looking up at a star so bright it fills half the sky, feeling the supersonic winds that circulate heat from the permanent day side to the permanent night side. Or imagine drifting in the cold darkness around Rox's 42BBA, where your sun is just another bright star among thousands, where a year lasts longer than recorded human history, where the only warmth comes from the planet's own internal heat, slowly radiating into space. These are alien environments beyond anything we experience on Earth, and yet they're governed by the same physics, the same gravity, the same quantum mechanics that govern everything else. As we look to the future, the search for giant planets continues. New instruments coming online will find planets in orbital configurations we can't currently detect. Long-term monitoring campaigns will discover cold giants in wide orbits. Direct imaging with next-generation telescopes will reveal planets around stars that are currently too bright or too far away. The record for the largest planet will probably be broken perhaps multiple times as we fill in the gaps in our surveys and explore new corners of parameter space. But more than just finding bigger planets, we'll understand them better. We'll measure their atmospheric compositions in detail, detecting molecules and elements that reveal their formation histories. We'll track their orbital evolution over decades, watching as tidal forces and stellar evolution reshape planetary systems in real time. We'll find planets around different types of stars, massive stars, binary stars, dying stars, and see how the stellar environment affects planetary properties. The giant planets we discover in the next decade will teach us as much as the ones we've already found, and they'll surely surprise us in ways we haven't anticipated. Here's what I want you to take away from our journey. The universe is vast and it's diverse, and it's constantly surprising us with its ability to create phenomena we didn't predict. The biggest planets we've found are remarkable, not because of their size alone, but because of what they teach us about physics, about formation processes, about the range of environments where planets can exist. Every discovery expands our understanding and raises new questions. Every answer leads to deeper mysteries. And perhaps most importantly, studying these distant giants gives us perspective on our own world. Earth is tiny compared to these gas giants, It's fragile in ways they are not. It has liquid water, a breathable atmosphere, and life things we haven't found anywhere else yet. By understanding the full diversity of planets, we better appreciate how special Earth is. Not because it's unique in any fundamental way, but because it's the only planet we know of where beings like us can exist to contemplate the cosmos. The search for the biggest planet is really a search for understanding. It's about pushing the boundaries of what we know, testing our theories against the extremes of nature, and constantly refining our picture of how the universe works. It's about humility in the face of cosmic diversity and excitement at the prospect of new discoveries. And it's about recognizing that we're part of something much larger than ourselves, citizens of a universe filled with wonders we're only beginning to explore. So, as you drift off to sleep tonight, let your mind wander among these giant worlds. Picture Tari S4b light as balsa wood defying our expectations. Imagine HAT P67b evaporating into space in a slow cosmic exhale. Envision Rox's 42b, a lonely giant at the edge of its system, born more like a star than a planet. And remember that somewhere out there orbiting a star we've never observed, there might be a planet even larger, even stranger, even more remarkable waiting for future astronomers to find. Thank you for joining me on this journey through the cosmos. I hope you found it as fascinating as I have, and I hope it's given you a sense of wonder about the incredible diversity of worlds that exist beyond our own. If you enjoyed this deep dive into planetary science, there are so many more cosmic mysteries waiting to be explored. Until our next journey together, keep looking up, keep wondering, and sleep well under the stars.